Since the dawn of human curiosity, the stars have served as a canvas for our deepest questions. We have looked upward with wonder, tracing patterns in the night sky, measuring the heavens, and gradually unveiling the vastness of the cosmos. Over millennia, the evolution of scientific tools, from the naked eye to sophisticated telescopes, has transformed our understanding of the universe from myth to measurable reality. Yet, despite this incredible progress, the universe continues to whisper secrets that challenge our very notions of physics, matter, and the fabric of space-time itself. One of the most compelling cosmic puzzles to emerge in recent decades is the phenomenon known as fast radio bursts, or FRBs. These are intense pulses of radio waves that flash across the sky for mere milliseconds, each releasing an enormous amount of energy, so much so that a single burst can outshine entire galaxies for the briefest instant. The discovery of FRBs has sparked a profound reevaluation of astrophysical phenomena, stretching the boundaries of what we thought possible and opening new windows into the universe. The story of FRBs begins with an accidental discovery. In 2007, scientists revisiting archival data from the Parkes Observatory in Australia detected a millisecond-long radio pulse unlike any they had seen before. This burst, initially thought to be noise or interference, was later recognized as a signal from far beyond our galaxy. This finding was a watershed moment. What had once been dismissed as an anomaly was now confirmed as a genuine, extragalactic phenomenon. The initial shock gave way to excitement and a rush to understand what could produce such a brief, powerful signal. Over the next years, more FRBs were detected by telescopes across the globe, from the Green Bank Telescope in the United States to the Arecibo Observatory in Puerto Rico. Each new detection brought with it new data, revealing that FRBs were not one-off oddities, but a population of cosmic events occurring regularly across the universe. The power of these bursts is astonishing. In just a thousandth of a second, an FRB can release as much energy as the sun emits in several days. Such concentrated energy output suggests that the progenitors of FRBs are extraordinarily energetic and compact objects. This has led scientists to focus on highly magnetized neutron stars, known as magnetars, as one of the most promising sources. Magnetars are the dense, collapsed cores of massive stars that exploded as supernovae. Their magnetic fields are trillions of times stronger than Earth's, creating conditions where starquakes and magnetic reconnection events can unleash colossal bursts of energy. The 2020 detection of an FRB-like burst from the galactic magnetar SGR 1935 plus 2154 provided the first direct evidence linking magnetars to FRBs, offering a tantalizing glimpse into the mechanics behind these cosmic signals. Yet, magnetars do not tell the whole story. The diversity of FRBs is striking. Some repeat with unpredictable patterns. Others show periodic bursts tied to rotational or orbital cycles, and still others remain singular events. This suggests that multiple types of sources or mechanisms might be responsible for different FRB populations. Models propose everything from neutron star collisions, black hole accretion events, to more exotic physics like cosmic strings or axion stars. Moreover, the environments in which FRBs originate are diverse and often extreme. Some have been traced to dwarf galaxies rich in star formation. Others come from the outskirts of massive galaxies, where older stellar populations dominate. Understanding these host environments is key to deciphering the astrophysical conditions that give rise to FRBs, informing theories about their origins, and the life cycles of their progenitors. Advances in technology have accelerated the pace of FRB discovery. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, telescope, with its enormous field of view and advanced real-time data processing capabilities, has dramatically increased the known FRB population, including many repeaters. At the same time, China's 500-meter aperture spherical radio telescope, FAST, offers unparalleled sensitivity, enabling astronomers to detect fainter and more distant bursts with greater precision. These powerful instruments allow researchers not only to detect FRBs, but to localize their sources within host galaxies, a process crucial for unraveling the physical mechanisms involved. Localization efforts have revealed that some FRBs are embedded in dense magnetized plasma environments, leading to the distinctive dispersion and polarization patterns observed in their signals. Beyond their enigmatic origins, FRBs have emerged as powerful tools for probing the universe itself. As their radio waves travel billions of light years, they pass through vast expanses of intergalactic plasma. This medium affects the burst's dispersion and scattering properties, encoding information about the distribution of baryonic matter, the so-called missing matter that makes up much of the universe's ordinary matter but remains difficult to detect through traditional astronomical methods. By studying the dispersion measures of FRBs, astronomers can map the density and distribution of ionized gas in intergalactic space, revealing the structure of the cosmic web, the vast network of filaments and voids connecting galaxies. This makes FRBs uniquely valuable for cosmology, allowing us to investigate the large-scale structure and evolution of the universe in unprecedented ways. But the mysteries and implications of FRBs extend beyond astrophysics into the philosophical and speculative. Some have pondered whether these bursts could be artificial in origin, signals, or byproducts of advanced extraterrestrial civilizations harnessing immense energy for communication or technology. Though there is no evidence to support this, the hypothesis reflects humanity's enduring fascination with the possibility of other intelligent life in the cosmos and highlights the importance of keeping an open mind in scientific inquiry. The study of FRBs also exemplifies the collaborative and interdisciplinary nature of modern astronomy. It brings together experts in radio astronomy, astrophysics, data science, and engineering from around the world. The enormous volumes of data generated by radio telescopes require sophisticated machine learning algorithms and supercomputing resources to identify the fleeting bursts amidst cosmic and terrestrial noise. International cooperation is key. Observatories across continents share data and coordinate rapid follow-up observations in other wavelengths, from X-rays to optical and gamma rays, to capture multi-messenger signals that might accompany FRBs. This holistic approach aims to build a comprehensive picture of the phenomena, combining timing, location, energy profiles, and environmental context. Looking to the future, the upcoming Square Kilometre Array, SKA, promises to revolutionize FRB research further. With its vast collecting area and exquisite sensitivity, the SKA will detect thousands of FRBs daily, enabling statistical studies that can illuminate population characteristics and their evolution over cosmic time. Complemented by space-based observatories and gravitational wave detectors, these efforts will place FRBs within a broader astrophysical framework. In the grander scheme, the search for the sources of fast radio bursts is a testament to the spirit of exploration. It challenges us to listen to the universe's faintest whispers, to harness technology and ingenuity, and to embrace the unknown. It is a vivid reminder that our cosmos is alive with phenomena that defy easy explanation, beckoning us to question, discover, and dream. As we continue this journey, every detected FRB is a messenger from across space and time, bearing secrets of cataclysmic events, extreme physics, and the vast cosmic web. They teach us humility, perseverance, and wonder, affirming our place as curious observers in an infinite universe.